welcome Dr. Art Shabalitwong. Thank you.
All right, thank you. First of all, I'd like to thank Dr. Manod for helping organizing this wonderful event, and it's very nice to see colleagues and friends and wonderful audience. Again, my name is Art Shabalitwong. Right now, I'm with Rutgers University. I'm going to be unemployed, so I'm moving to University of Washington in next month or so. So today, I choose a topic to talk about the optimization. The content of this presentation might be slightly different from what was presented in the morning. In the morning is more of the transportation, what people think and how people model transportation problems. Okay, but my background is in operation research, optimization to be specific. So we look at transportation as one problem, and we try to do our best to solve a particular problem and try to be able to come up with decision-making models to help them come up with good solutions. Okay. So again, I have a bunch of mathematics here, but I will try to cut it as much as I can. It's hard to to be between lunch and afternoon nap, so just bear with me. So I'm going to pick three topics that I worked on for the past 4 or 5 years. One is airline-wide optimization. It's about transportation, about air transportation that involve airline industry. And the other topic is going to be on collaborative decision-making to resolve flight conflicts. It's more of the transportation from the policy-making perspectives as opposed to the end user or the enterprise perspective. And if I have time, I would share with you on the crude oil transportation based on my experience at ExxonMobil. So I help them with solve some transportation problem. Okay, so with the airline-wide optimization, I'm going to talk about a couple of problems. One is aircraft maintenance routing, which is one of the hot topic in airline optimization. It's the work that Ajahn Mano has been doing it for a long time. And the first paper, pretty much the problem that I'm working on with my student, and then we extended to integrated problem. So just to give you some sort of motivation of this problem, right now the airline industry has been growing. It's been growing very fast, rapidly over the past few years, despite economic downturn. But again, in the U.S., each airline operates about 5,000 flights per day, and offering 4 million fares, serve over 10,000 markets in the U.S. alone. And I just took an article from last year from USA Today. I quoted, millions of passengers have been on at least 6,500 U.S. airline flights that shouldn't have taken off because planes weren't properly maintained during the past 6 years. So again, as the market grows, maintenance has become a key because you have more demand, you have to utilize your resources more and more. And again, once the resources are utilized, you need to maintain your resources. Okay, and maintenance was a cost factor of finding in 18 air traffic accidents since January 2000. And about 40 people died and 60 people injured. So just to give you an idea of what airlines would do in terms of aircraft maintenance. Everyone fly every day, but we don't really see how they're being maintained and what kind of thing that would be involved. Again, different countries and airlines have slightly different requirements to maintain the aircraft. And there are several types of common maintenance for U.S. domestic airlines. We call it Type A, Type B, and Type C. Type A usually be done every 65 flight hours, so usually once a week. This is the regulation imposed by FAA or Federal Aviation Agency in the U.S. And Type B is a little longer, every 300 to 600 flight hours. So you can imagine this maintenance is more like your car, how you drive your car, and how often you change your engine oil, how you check your timing belt, inspection, or what have you. Okay. So again, maintenance is very important. And what we want to focus on in the problem that I'm going to present it to you today is about Type A maintenance check. Just to give you an idea of what airlines do in the planning. Okay. So basically, this is pretty much the breakdown of operation research problem that arise in airlines industry. Okay. So the first problem is called fleet assignment. So you imagine if you're operating an airlines, you have to figure out what fleet, what type of aircrafts to be assigned to what flights, what legs, okay, what OD pair, if you will. And this is planned months before the flight become operational, okay? And then about a month or so, which kind of varies, a month could be 2 months, could be 3 months, and the airlines plan the routing of the aircraft, okay? So once you figure out what aircraft go to what flights and how you're going to route them, that's another issue. And when you route them, you have to make sure they would go through a sequence so that they can be properly maintained, okay? And then the next step is about 1 or 2 months before, then they would assign the crew. This is what we call crew scheduling problem, okay? So in this problem, I'm going to talk about the Type A that's required by FAA. So it's a Type A that would require about once a week. But again, airlines have stricter and more often Type A checks. For example, they might want to do it every 4 days or so because even though the deadline, like all the hard timeline is a week, but you don't really have to push to the end because the effect of the improper maintain could be much larger than you maintain it more frequently than you have to. Okay, but the key is different locations may have different costs of maintenance. For example, if you want to maintain an aircraft in JFK, New York, versus maintain an aircraft in Phoenix, in Arizona, of course the cost is going to be different. So just to give you an idea what kind of problem that arise every day that airlines have to solve. So given a daily flight schedule, so you can imagine you have different flight from A to B, different schedule, different legs, okay? So the problem is as follows. One, you given a fleet of aircrafts, assuming that you have already made decision in terms of fleet assignment. Okay, so you have limited in-fleet sites, and you have a set of flights or legs, okay? And of course, each flight would need to be covered once. Basically, you need to assign one aircraft to this leg, for example, this one. You're not going to have two to fly on the same legs. And the goal is to meet the maintenance requirement and also to maximize the revenue and minimize the cost. And the routes have to be cycled, for example. If end at JFK, it has to start from JFK, right? So you cannot fly from JFK to Phoenix and then you have another same plane starting from JFK again because it has to begin where it ends. Okay, and there's no empty aircraft in the air, so which is different from taxi or bus. So just a traditional way. So again, when it comes to how we solve the problem, I'm going to be quite abstract in that sense because we don't want to get into the details, but I just want to sort of narrow it down to you how one can solve this real-life problem and how to use operation research tools to go about solving the problem. So for example, if you have a bunch of flights, okay, different time, different legs, what people do, how we can model this problem is we do the time space and building an island and node aggregations. Because the time between 8:45 and 9:30, we can call it an island here to build a network, if you will. Okay, and this is a very standard way of people in operation research would do how to model this aircraft routing problem. Again, it doesn't have to be just aircraft. It can be any kind of routing problem. It can be bus routing. It can be any fleet. It can be vessel. It can be anything. So once you have this time-space network with island isolation, then you can come up with this type of representation of your problem. Okay? And then I just want to give you, for example, if you see this representation, you might not be able to see, okay, what kind of solution? What do they have to come up with as a solution to this problem? How can you go about and routing these aircrafts? Okay? So again, one big assumption is you have daily schedule. It means that if you're an airline, you're going to fly these legs every day. Okay? So the question is, okay, how many aircraft do we need here to fly this? At least one, at least two, right? So you can do counting. The question is, how many aircraft do you need? And how are you going to route them? Because there's many possibilities. You can route from here. Oops, sorry. So you can go from A to B, then you can go from B to A back here. Or you can go A to B here and B to A right here. So there are many possibilities. One solution could be, in this case, we have a legs from JFK to Washington, D.C. to Dallas. Okay, so one solution is to have 3 aircrafts with 3-day maintenance. What do I mean by 3-day maintenance? It means that it takes 3 days to fly an aircraft, and then you put the aircraft back to the maintenance station at night. So one solution could be have one aircraft assigned to B and C and go to F. And for the other days, have A and G. The other one have D and E. Okay, so this is sort of representation. So you can see that every day you're going to have aircraft 1 flying from B, C to F. And you have aircraft 2 to A to G. And aircraft 3 from D to E. So this is an example. But if you have 2-day maintenance, for example, you put a stricter rule that, look, you cannot fly more than 2 days without maintenance. Then one can come up with a solution such as A to G, and you have one flying F, and B, C, and E, D, and E. So meaning that you're going to have a sequence of A, G, B, C, which require 2 aircrafts. So every day, aircraft 1 going to fly from A to G and G, and aircraft 2 going to fly from B to C, and F, D, E. So it means aircraft 1 fly from F, and the other one D to E. So this is a general solution that one can see. But the question is, how do you know this is the best solution? So how do we figure out that this is the way to minimize the cost? This is the best way to utilize your aircraft, for example. So that's where we come in as an operation researcher. We try to build a model. We try to use mathematical models to represent this problem and to come up with a way to optimize and minimize the cost. So this problem is called aircraft fleeting and routing problem. So this one of the seminal work in 1998 by Cindy Barnhart, Ottomano advisor at MIT, came up with a way to model this problem. It's called flight string models. Okay. For example, it's naturally, as you can see, that aircraft go from B to C to F. So you can think of this as a sequence of string. So these represent possibility of where to go for this, where each aircraft would need to go. So this would be represented as a string. And each string has its cost because it will tell you, okay, where you're going to have your maintenance done. Then you know the cost at that station. And if you connect the flight, for example, flight from B to C, as it turns out that the duration between B and C, that by the time that B arrives and by the time that C leaves, is only 30 minutes. So it's not good. So it's not a good legs to begin with. So we might have to penalize because there's a short turning period. So there's many ways to represent this problem. And one of the work, like I said, to use flight string model to solve the problem. So, and then we, with my student Zi Liang, who's now at Peking University, and we talked with Hui Shen Huang from NUS and Alice Johnson. So we chat and we came up with a better way to to somewhat model this problem. Like I said, one way is you can look at this sequence as a string, and we ask ourselves, is there any better way to represent the problem? So what we did is we saw that, well, we can break this down into a cycle, if you will. So we said, look, this is a network problem. Can we come up with any kind of network representations? So we proposed what we call the rotation tour network. Okay, what we did is, like I said, I don't want to bore you with the detail, but the idea is very simple to us. Is you have this tour, all we need to do is add a wraparound arc for the maintenance to go back to the beginning, so that we can count the number of planes that we need to fly for that particular legs. And this is an example for 3-day maintenance. This is an example of 2-day maintenance. So you can have different wraparound arcs, and you can represent this problem mathematically. So, given a daily flight schedule, what we do is, first we transform the network of daily flight, JFK, Cincinnati, and Memphis. For example, if we need 2-day maintenance, what we do is we're going to duplicate this network for 2 days. Everything going to be the same, but if you see something in common is, okay, the flight that's flying on day 1 going to be different from day 2 because that represents a sequence. Okay, so in this case, this is one solution of our network representation. You can have one starting from JFK, go take E, go to A, and come back and being maintained. The other aircraft would be B to C to F and go back. So it looked a little bit confusing, but this is a cycle. This is a tour. And what does a tour mean? It would mean that we need to have 3 aircrafts to fly. So again, once you have the network here, basically you have to assign an aircraft to every leg, right? So in this case, I'm going to have a green aircraft that fly E1 only for day 1, and have another aircraft to fly AD here on day 1, and another aircraft, red one, B, C, and F here on day 1, and it will take turn because it become a tour. So B, C, and F, so this guy would fly E2 for the second day, so which is the same as the green. So the green would fly the same A and D as the blue one. So it become a tour. So the reason that they want to do it is because to share the utilization of the aircraft. So they have a proper wear and tear. So again, the idea is very simple, is to add a wraparound arc and come up with the solutions. So what we do as an operation researcher, we try to build X, Y, and Z to make good decisions. So we can build this mathematical model. And the idea is, again, just excuse me with all the Greek letters, but the whole idea is to minimize the through value, meaning that the connection that you would make money, and the short connection, so you want to penalize. And you need to have what we call constraint. Basically, each flight on a particular day need to be covered exactly once, and we need to have flow balance constraint. Whatever flight flying to what stations, we can have the same flight going out. And we count the plane, how many planes are there in the system, and we have the maintenance capacity for each station. For example, for Memphis, you want to make sure that, okay, capacity is 1, you can only maintain 1 aircraft at that time. So this is an example of how we can build optimization model, taking real-life transportation airlines problems. Again, this is an example of how we can come up with flow balance constraint. Basically, a node is a depart and arrival event at a station. So it start and end up wrap around arc, so we can build these simple equations. And we can do the plane count. We can count how many planes we have, and we can do capacity counting. So here's how we calculate the profit. So for certain connections, we can say that, well, if you make connection in Dallas, there's a lot of people flying from JFK to LAX, and as it turns out, you have a lot of demand from JFK to LAX, and this connection is what most people would need to make to fly from New York to LA. So then this is a good connection, so you would give a true value to the connection. So it's something that you want to choose, and you can penalize a short connection. Basically, if you fly here and you have very short turnaround time to catch a flight, then it's not good. Then you want to penalize it. So we took case studies, 4 cases from AA, American Airlines, and we somewhat kind of anonymized the data. So we have 4 size of the network. So we start looking at the fleet of 14